And so today we would ideally cover two sections because we're quote unquote day behind. The first section we're going to do, and we'll probably cover the entirety of it today, is imaginary numbers. And yeah, truth be told, as far as just amount of content, there's quite a few things we have to go over. The good news is the next section can be covered in one slide. So maybe if for some reason imaginary numbers is clicking, we'll get to this. If not, I can lump this into the next section, and might be a little bit behind, but it's not like we're going to be sprinting the entirety of the semester to catch up. So if you watch both videos, great. Maybe the second video will be helpful more next week as opposed to the imaginary numbers video. It is super helpful because it's one of those that if you've seen it before, it's not too bad, but if you've never seen it before, it's a little bit weird of a concept. We're starting to deal with things that don't behave like normal numbers. Okay, so for starters, someone tell me what I is. What does I equal?
The square root of -1.
Great. And so the whole logic behind it, I think it was Newton, but I'm not really sure. Someone can Google it and double check that, is that we deal with this. We see square roots of negatives. We've seen them a couple of times in this class, and we kind of just stop and say, I don't really know what that is. I can't really do that. I don't get a real number. But Newton said, okay, but what if there is? What if I is equal to the square root of -1 is actually a thing that we can deal with? And it turns out that if we make kind of that assumption that it's something, we can do a lot of things with these square roots. We can start to do multiplication, division, addition, subtraction, stuff like that. And by the way, a question on the next exam, I'm already going to say it, I'm not going to write it down, is that the whole goal of this section is to, well, introduce imaginary numbers, but to show that we can add, we can subtract, we can multiply, we can divide, and we'll always get something like I is going to be there, or more specifically, there's going to be a lot of spam calls lately. More specifically, it's going to be in this form. So that's an imaginary number. A complex number is something that looks like this. So that will be the answer to a question on the exam. Why do we add this way? Why do we subtract this way? Why do we resolve this thing? We want to always get an answer as a complex number. Cool. So if I'm just asked to write something in I notation, let's say I have the square root of -9, up to this point, hands are tied, I say no real solution and I stop. But now that we know what an imaginary number is, I can actually break this into pieces and say, yeah, I can't really take the square root of -9, but I can break it into, let's say, square root of -1 times square root of 9. And I know that the square root of -1 is I. I know that the square root of 9 is 3. So I would get I times 3. And that's my final answer. But usually when we deal with like x's and y's, we don't do like x times 3. We write it as 3x. So here we'll write it as 3i. I wouldn't really dock you if you wrote it like this on the exam. It's not highlighting what I want to. That on the exam, but typically we write number and then the imaginary number. Great. Question 2, exact same concept. I have the square root of -3. Don't know what that is, not a real number. I'm going to adjust it as and get I times the square root of, square root of 3. And now here, square root of -1, getting ahead of myself. And so I know that the square root of -1 is I. And the square root of 3 is something that we can just go ahead and throw into our calculator and say, Okay, I get, I don't know what it is, 1.3 something, blah, blah, blah. But that's an approximation. If we don't know what this is, if this isn't a nice number, then we kind of just leave them alone and say, yeah, okay, my exact answer is going to be I root 3. Now, someone asked in the chat, why don't I just leave this as -1? And I'm not sure if this is going to answer your question. So if it doesn't, let me know. Well, or sorry, square root of -9. I want to simplify it. I want to get it into a term like this, because once I get it into 3i, until this imaginary notation, well, then I can start to add imaginary numbers or complex numbers. I can multiply, I can divide them. So for starters, it seems arbitrary, like why am I doing the simplification? Fair, but it's going to have some value, honestly, on the next slide. Does that answer your question? I'm not sure it does. Yes, yes. I don't want a square root of a negative number because I can't do anything with that. That is no real solution. So I want to kind of alter it slightly so that I can do something with it. Cool. So just like I claimed, let's move on to this next slide. And now I'm multiplying these two square roots of negative numbers. Well, I can't do that. Like, that's not a real number. That's not a real number. I can't do anything at this point. I would just stop if I didn't know about these magical imaginary numbers. But now I know from this previous slide, I can simplify each of these roots. So what does the first root simplify to? What would I break my first root, this guy, into? What are the two pieces?
I square root of 2.
Yep. So you're getting a little bit ahead of it, but yeah, it's the square root of -1 times 2. And exact same thing for the next one. Square root of -1 times 2. And well, we know what the square root of -1 is. It is I. So we get I root 2 times I root 2. Great. And so now that I have this negative outside the root, so I had a square root of -2, now it's I root 2 times I root 2. Now I am allowed to multiply. Since this is a positive square root, well, we've seen positive square roots before, and if they're the exact same root, we're allowed to multiply what's under each square root. So then this problem becomes I times I is I squared. That's kind of just basic variable stuff. Square root of 2 times the square root of 2 gets the square root of 4. And square root of 4 is 2. Okay, so back to the question that is going to now be a free point on the exam. This is not a complex number. To pull over the definition of a complex number, it's this: something in this form where I have some sort of a and some sort of bi. So if I did 2 plus 6i, that is a complex number. I have a real number, another real number, and an I next to it. Notice how in either form I have no I squared. Oh, I don't want to leave it as an I squared. So what is I squared equal to?
-1.
Mm-hmm. I squared is -1, which makes sense if you think about it for a second, right? We have the square root of -1. Well, if you square something, you remove the square root. So square root of -1 squared would just get me -1. And so that is why we can't stop here. This is not a complex number. Now, once I resolve the 2i squared, I get 2 times -1, which is equal to -2. And so it doesn't look like a complex number, but it technically is. It's just the a part. The b is 0 in this case, but it is a complex number. So in this case, I took two imaginary numbers / complex numbers. I multiplied them. I got back a complex number. That's the big result. Now you might be asking yourself, why couldn't I have just multiplied these at the beginning? Right? I have two square roots. I have a negative number. And so what would happen is seems like I should be able to just multiply whatever is under the square root. So that would get me square root of 4. Well, that's equal to +2. So we have to be extra careful. It seems like I'm doing unnecessary steps here to go through this whole, put it as an I and then multiply the i's and then resolve the I squared. But if I don't do that, I'm not going to get the correct answer. 2 is not correct. The correct answer is -2. And that's because when we have these imaginary numbers, when we have these negative square roots, they don't behave normally. So that's why we need to resolve the I first. How does everyone feel about this first example? Well, I guess this is the third example technically. Great. So someone walk me through how to do 2.
I'd write out -1 and then square root of -1 times square root of 2 times square root of -1 times square root of 3.
So you'd put a -1 in front?
Yes.
Okay, that's fine. I wouldn't do that, but if it helps you keep track, that's perfectly fine. But I like how you didn't say, okay, I have a negative here. I multiply that inside my root. I can't do anything to the square root of -2 until I resolve that -1 being pulled out. And additionally, I can't really do anything here as well, because if this is outside my square root, this -1, I can't multiply it inside the square root because I have that square root barrier. I can't just move things inside the square root arbitrarily. Okay. So then I have -1. I know that the square root of -1 is I. So -1 I times square root of 2 times I root 3. Maybe just to keep things straight, I'll just put a times here. Okay, what do I do now?
So we'll end up with an I squared, which is -1. So -1 times -1 will give us +√6.
Yep, so I'll break that down into maybe an additional step. So I times I is I squared. Now that I have the square roots removed from my, my -1s removed from my square roots, then I can multiply them together to get a √6. So now it seems like I'm being a little bit hypocritical. Okay, I'm taking something, I'm multiplying it into the root. The reason I'm allowed to combine those is, first of all, they're not negative square roots. And second of all, they both are in a square root. So I can't bring the -1 inside the root because it's by itself. There is no root. I can here because they are both square rooted. Okay. And then as John mentioned, okay, well, I squared is -1. So my problem becomes -1 times -1 times √6, which, well, it's just √6. And √6 is not a nice square root. And if you're thinking to yourself, how do I know that this is not a nice square root? Well, it's fine to use a calculator there and say, okay, maybe that is good. Maybe that does give me a nice whole number of 2 or 3 or whatever. If you plug it in, you'll get, in this case, 2.3 or something, 2.2 maybe. Great. Any questions about this? Oh, I should just remove this because this is unhelpful and incorrect. Okay. One more of these imaginary numbers, but now we're doing division. So someone besides John walk me through this problem. If you need a hint, I don't like that on the bottom.
So would you change it into root 27 divided by -1 time with root 3
Mhm.
or root -1, my bad, with negative root 3?
Yeah.
Or 3, I don't even know what I'm saying.
I think I get what you're saying, though. We'll see. Maybe not. Looks weird. It'd look better if I make it bigger. Not really. Oh well. Yes, so first thing to deal with, I have a negative square root on the bottom of my fraction, and I don't like negative square roots, so I pull out a -1. And my next step would be to change that -1 to an I. Oh, it's just getting worse. I'm just going to start a new equation. Back on track. Totally worth it. So I'm going to change this square root of -1 to I. By the way, if you start to get comfortable with these complex numbers, there is the shortcut of every time you are removing a negative under your square root, you're always going to pull out a -1. So you're always going to get this result. So you can kind of skip from step 1 to step 3 if you want to. I'm aware that you see a negative square root. So, well, it's going to be I times that square root. Okay. Now that I have it in this form, notice here, I don't have a negative square root anymore. So if that's the case, well, I can divide, just like I could multiply. Oh boy, what did I just do? Okay. I can go ahead and divide. Square root of 27 divided by 3 gets me the square root of 9 on the top. The square root of 3 goes away on the bottom. I don't know why the equation editor is being mean to me this morning, but that's fine. So then I have the square root of 9 over the square root of I. What's the square root of 9?
3.
Cool. So then I'm just left with 3 over I. This slide is something else. Yes, the last part doesn't look too bad. And now, yes, if you have some experience using imaginary numbers, we typically don't like the I on the bottom, but for now, we'll talk about this later in class, but for now, I'm not concerned about that. Really, the whole purpose of this slide is to say, oh, if I have a negative square root, and I want to multiply or I want to divide, I have to first make sure that I resolve the negative square roots. I turn them to I root 3, or here we turn them to I root 2 and I root 2 and I root 3, so that I can get a result like this. If I have an I squared, in order to make sure that I get a complex number at the end of the day, I have to turn that into a -1. Any questions? Okay, one more example and then I'll let you guys loose to practice. So now we are getting into this official complex numbers. I already hinted at what the definition of a complex number is. It is something of this form. I'm going to have a real number plus a real number times I. So this is a complex number. 2 plus I. This is a complex number. 3 minus 3I. So I should get my claim and my big kind of free point on the exam. I should be able to add and subtract complex numbers and get a result that is, well, it's either a complex number or just has a single I or just has a single letter. I don't want any I squareds, I cubes, any of that flying around. And so of the operations, addition's pretty simple. I mean, simple is always a dangerous thing in mathematics, but I almost kind of think that they're not really complex numbers at this point. Like if I adjusted this problem like this, that should be pretty solvable for you guys. What I do is I distribute that negative to both things on the right side, and then I combine like terms. Use the exact same logic here. So I have 2 plus I at the beginning. I'm going to leave that guy alone. There's nothing in front of him. So I'll just get 2 plus I. Might have said 3I. It's just 2 plus I at the beginning. Here I have a negative in front. So I'm going to distribute that to both terms. And I'll get minus 3I. Oh no, sorry, minus 3 plus 3I. And now I combine like terms. So what's my final answer going to be?
Four I minus 1.
Yes. And again, this falls into the category of if you wrote that on the exam, you're getting full points. I'm not going to dock you. Usually when we write complex numbers, we write the thing that doesn't have the I first and then the thing that does second. So you'll probably see it like this. I'm good with either one. And that's it. If this was addition, the only difference between addition and subtraction is, well, with addition, I don't even need to distribute a -1. I just go ahead and drop the parentheses, combine them, and I'm good to go. So of the operations, we're going to see multiplication, we're going to see division. Addition and subtraction is almost so simple that usually students think, oh, that can't be it. I have to multiply everything out. I have to FOIL it. I have to do something more. No, really, you either have to distribute -1 and combine like terms, or just immediately combine like terms and you're good to go. Any questions about this? Cool. Let's take a look at the assignment. We are in page 10, probably. Okay, so this was the first slide. Make sure you can do it, super important. This was the multiplication and division. Maybe there will be one question on the exam. This is more, do you understand how to change it into an I form and then continue from there? Certainly questions on my math lab. And then you should be able to do, it looks like everything on the first page. So don't go into multiplying complex numbers, but everything up to there should be doable. Any questions about this, about content, about the take home before I put you in your breakout rooms? Okay, so we went through kind of an introduction of imaginary numbers. We did adding or subtracting complex numbers. So we're going to continue into multiplying and dividing complex numbers. And so multiplying complex numbers, kind of similar to addition and subtraction. I'm just doing basic multiplication here. The only thing I'm going to watch for is at the end of the day, if I have an I squared, I'm going to change him into that -1. I'm not going to leave him as an I squared. See that in practice here. 4I times I Well, that's just 4i squared. I would do the exact same thing if it was 4x times x. The additional thing I have to watch for is, well, I squared is just -1. So my final answer is -4. Same thing here. Question 2, I use the distributive property. Just as though if I were dealing with variables. 3i times 4 is 12i. 3i times 2i is 6i squared. Now, what do I do?
Turn the I square into -1.
Mhm. So my final answer, if I want to write it in the correct order, is -6 plus 12i. As Austin mentioned earlier, you could write this as 12i minus 6. Technically, it's correct. We just more often write it in this form of number, and then imaginary number is tied to the second one. Great. So notice here still, I have a complex number at the end of the day. I multiplied two complex numbers. I have a result of a complex number. So what I want to show, I wanted to show with addition, subtraction, multiplication, division, at the end of the day, we will get a complex number if we are multiplying complex numbers, or adding, subtracting, so on and so forth. Okay, so notice here, I have 1 plus 2i, I have 1 minus 2i. When I have this thing of this whole thing is the exact same thing as this second binomial, the only difference here is the middle. Does anyone know what we call those things? This pair of things. They're related somehow, and they have a fancy name about how they're related.
Something.
Yeah, close. Contra something.
Conjugate.
There we go. What a conjugate is specifically is if I have something like C plus DI, its conjugate is whatever has the I flip the sign in front of it. So those are conjugates of each other. C plus DI and C minus DI are conjugates. 1 plus 2i, 1 minus 2i are conjugates of each other. And sure, sometimes in math, we just like to give fancy names for the sake of giving fancy names, but keep in mind that we're going to get an interesting result when we go through this process. So here I am going to FOIL. And by the way, this is what I'm talking about when people have a question like this. I'm going to erase it, so don't put this part in your notes. People, we learn how to do multiplication of complex numbers. And when we see this addition problem, our brain panics again and says, oh, it can't be that easy. I can't just go ahead and drop the parentheses. I have to do more. And we start to multiply things out. Make sure you're checking to see, is there something between the two? If there is, you're probably going to multiply, or you're probably going to add or subtract. If there isn't, like we have here, I have nothing between my two parentheses right here. Just have the two things. That's when we multiply. So watch for that. That's a very common mistake I see. And foiling 1 times 1 is 1. 1 times -2 is -2i. 2i plus 1 is positive 2i. 2i times -2i gets me -4i. Great, what do I do now?
Just cancel out the two i's in the center.
Sure, you can do that. I have a -2i, I have a positive 2i, so those certainly go away. I change color, but whatever.
Put the -1 where it's squared.
I get 1 plus 4, which is 5. And this result, this thing that I have no i's, right? Or maybe no imaginary numbers in my answer. That's why these conjugates are so powerful, is that if I multiply any conjugate or pair of conjugates together, I'm always going to get something that doesn't have an imaginary number, that has a real number. Here it's 5, I could have 8. I'm not going to have this bi part of my complex number.
Sorry, I got lost in how you get negative 4i squared.
2, that's 2i times negative 2i. This guy in the foiling process specifically.
Oh, you have to multiply them as well. Those two. Okay.
Any other questions? Cool. Now, you might be thinking to yourself, why? I mentioned that these conjugates are important, so I better have some reason to back that up of why is it actually important? When am I actually going to use this, at least in the sense of complex numbers? And it's here. So sometimes when people ask this question, this is division. So sometimes this question is just written like this. Just divide the following problems or problem. You could see that before. I wouldn't be surprised if my math lab says that. I'll try to avoid writing it like that on the exam, but technically what we are doing is we are dividing complex numbers. I don't like to use that term because almost zero part of this process has to do with actually dividing, but that is what we're doing. But at the end of the day, what we're trying to do, maybe it's not rationalized, I think I'm mixing that up. But at the end of the day, what we're trying to do is we don't like this in the denominator. And why do I not like that in the denominator? Kind of a broken record at this point. If that is in the denominator, I don't have it in this form. I don't have this nice a plus something I in just a regular sense. I have an I on the bottom of my fraction, so I don't have it in that form of a complex number. So the whole purpose of this process is to resolve that issue. I don't want the I in the bottom. Does anyone have any ideas about how I might avoid this issue or resolve this issue, I guess, more technically? No, I'll be right back. So I can't leave windows open in my house. Okay. Any thoughts? Any ideas? I want to make it so I don't have an I in the denominator of my fraction.
Would you do the opposite, like 3 minus 2i?
Mm-hmm. Yes. So I'm going to multiply the bottom by the conjugate. And since I'm dealing with a fraction, if I'm doing something to the bottom, I better do it to the top. So for the notes, let's say. And I'm always going to do it in the denominator. I don't care about the numerator. If there's an I there already, great. That saves me some steps. I only want to avoid dividing by I. So to do that, I multiply by the conjugate. I distribute, so 3 times 3 is 9. 3 times negative 2i is negative 6i. 3 times positive 2i is positive 6i. 2i times negative 2i gets me negative 4 squared. On the top, 6 minus 4i. So my top's not going to simplify any further for now. What does my bottom simplify to?
Would it be 9 minus 4i squared? Or
So my 6i's cancel out, negative, positive, which should come as no surprise. If they didn't cancel out, I didn't actually get rid of the i's. I didn't use the conjugate, or maybe I multiplied it correctly. So my 6i's cancel out. Okay, now what do I do?
to turn the I squared into a -1?
Yep. So I get 6 minus 4i over 9 minus 4 times -1 gets me 9 plus 4. I get 6 minus 4i over 13. Now, honestly, if I hadn't taught this class in the other college algebra class at CCD, I don't know, 20 times at this point, I would stop here and say, cool, I don't have an I in the denominator. I went through this whole rationalizing process. I'm good. 6 minus 4i over 13. That's correct. Honestly, I would probably give you all the points on the exam as well. But technically, that's not in this form. It's very close, but it's not a complex number. And so what my math lab will probably want and what is technically correct would be 6 over 13 minus 4 over 13i. So all I did is break up my fraction into 2 pieces. I don't really do anything in this step. If there is any simplification of fractions you can do, you should. And here I can't, so that's my final answer. Any questions about this?
Is that I not attached to the 4 anymore? It's just attached to the fraction 4 over 13?
Yeah, so again, technically this thing, what I just wrote, is the same thing as what you were saying right here. Yes, that's correct. That is not a complex number. Maybe I don't want to box this because it's giving me something weird looking. Technically, that is a correct answer, but 4i over 13 is the same thing as 4 over 13 times I. These are equal to each other. That's how we multiply fractions. So that will make it so it is in this form, which is one of the big themes of this section. I want to get an a plus b I. Maybe those are fractions, maybe those are decimals, that's fine. But I want the I to kind of be next to this b as opposed to being in the actual fraction. Does that make sense? Cool. Any other questions?
So is it fine if you leave it like 6 minus 4i over 13, or is it the other way technically correct?
The other way is technically correct. I would give you points either way on the exam. I don't know if my math lab's as kind as I am. It usually isn't, but I'm fine. Like I said, if this was the first or even the fourth time teaching the course, I would have stopped where that check mark is. Technically, that's not correct. I should go the additional steps. But I give you credit for either. Great. So we have only one more concept in the section, so I'm going to power through it and then let you guys practice these last two things before calling it a day. I did not get into the last section, which is no surprise to me. But since I am kind of powering through this concept, this is going to maybe seem like I'm leaving out the why of why is it okay that I'm doing this process. I go through it in much more depth. I think at the end of the video, it's probably the last concept I cover, just like it's what I'm doing here. So if you're not really tracking with the, oh, I don't really get why he's doing the process, I give a much better explanation in the video. Okay, so Last part here, this is clearly not in the form of this. I don't have an I to no power. I have an I to the 23rd, an I to the 60th, and I to the 70th. It's not going to be in this form, even though this is, as we maybe know or maybe have forgotten, anything to a power is multiplication, right? Like I to the 23rd is just I times itself 23 times. I cubed is just I times I times I. So this is multiplication. My claim, or what I want to show throughout this section, is I want to show that any multiplication, division, addition, subtraction, I should get back to this form. And so I can't just leave it like this. I can't leave it as I to the 23rd. Well, let's just talk about I again. So we know that I is the square root of -1. We usually just say, okay, I to the first is just I. If we want to write the square root of -1, that's fine, whatever. We also know that I squared is equal to 1. Talked about that. I cubed. Well, I cubed is just I to the first times I squared. Well, I squared to -1, so this is just negative I. -1 times I is negative I. I to the 4th is equal to I squared times I squared, which is -1 times -1, which is just 1.
Isn't I squared equals to -1?
Yes, so I squared is -1, so then I would get, oh, sorry, I see what you're saying right here. Yes, apologies. I to the 5th. Well, that's just I to the 4th. I to the 4th is 1, so we get I. Notice here that these match. Okay, we'll do one more. I to the 6th. Well, that's I to the 4th times I squared, which is I, or no, that is 1 times -1, which is -1. Notice how these match. Talk about these results. And so actually this continues. I to the 7th is -I to the 8th is 1. I to the 9th is I to the 10th is -1. I get this cycle of 4, a pattern of 4. It keeps going on and on and on. And so what I could do to find I20 to the 23rd, and this is a strategy that some people post online, is, okay, how can I put these pieces together of I to the something times I to the something times I to the something gets me 23rd, and all of my building blocks here are these things. That's a kind of assuming that you're really good at weirdly piecing together numbers, and that can get pretty cumbersome if I give you like I to the 5,000th or something like that. So the strategy I use, and I do this in the video as well, is I say, okay, I notice that I have cycles of 4. I have patterns of 4. So if I can figure out where my number falls into this cycle of 4, well, I can just write that as my answer. So what I'm going to do here is I'm going to say, okay, I want to find I to the 23rd. So I'm going to put 23rd, 23. It's a weird division. Let's try that again. And since I have these cycles of 4, I'm going to divide by 4. How many times does 4 fit into 23? 5 times. So I have 5 with a remainder of 3. Now the remainder is the key to my answer. If I have a remainder of 1, my answer will be I. If I have a remainder of 2, my answer will be -1. If I have a remainder of 3, I have an answer of -I. And then it seems weird, like it seems like my remainder should be 4. Well, I'm dividing by 4, so I should have a remainder of 0 in that case. My answer is 1. So that's the process, is I divide my answer by 4. I look at the remainder, and then I say, okay, well, these are my only possible values. I'm either going to get an I, a -1, a negative I, or a 1. Remainder is 3. So that's my answer. As I mentioned, I go into this a little bit more in depth in the video. I do a slower example. I justify my reasoning. So if you didn't track with this, I get that it's pretty weird. It's different from almost everything we did in this section. Definitely watch that video. I mean, you should be watching all of the videos anyways. That's it for the section. I would recommend practicing this on your own, but since we only have like 7 minutes left in class, I'm just gonna call it there and say use that 7 minutes to watch or rewatch the example with these certain powers, or use that time to kind of practice these two, multiplication and division. I can't really see that with all those things there. This rationalizing denominators and multiplying complex numbers. There's probably going to be one of each on the exam. So, and one of these two, but that's almost free points on the exam. So that's good news. You should be able to add and subtract complex numbers pretty easily. And then this section I'm going to go over next week. Watch this video though, because this is, remember when we did polynomial graphs where we said, okay, let's start with just intercepts. And now let's talk about zeros. Now let's talk about end behavior. That's exactly what's going to happen here, is we're going to build. We're going to say, okay, just start with intercepts, make sure we get these asymptotes right. Do we know what's happening at the asymptotes? And it's going to build to drawing a graph, which is arguably one of the more complex things, most complex things we do in this course, no pun intended. Any questions? Cool. Well, submit what you did today, probably at least up to maybe addition and subtraction of complex numbers. But even if you didn't get that far, because I didn't give you a ton of practice time, just go ahead and submit what you have completed in whatever week we're in, week 10. That seems far. Maybe that's right. Week 10, assignment 2. And then don't forget to do the out of class or the take home part of the exam to kind of clarify. I had a question in the groups. But when I say up to 4 hours, I'm not saying you will take it for 4 hours. Some people will get it done in 30 minutes. Some people will take 4 hours. If you're like me, you might take 6 hours just because I'm very paranoid and like to double and triple check my work and I have to make sure I'm understanding it. But don't, if you sit down and you knock it out, and honestly, maybe some of you might be able to knock it out in 20 minutes, don't panic and say, oh, he said it should take 4 hours. I'm missing something. You might not be missing anything. You might have just been paying attention when Rachel went over it. Cool. Well, if there aren't any questions, my office hours start in 5 minutes. I'm going to stop my recording.